Hello, everyone. Welcome to the Math Magician's Den. We are again going to talk today about limits at infinity and negative infinity. Now, if you watched one of my previous videos, you saw these rules for rational functions. First rule is if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is zero. If you have any rational function, remember what it is. It's a polynomial divided by a polynomial. And so if the degree of the top is less than the bottom, the limit is going to be zero. And again, you're going to have a horizontal asymptote, y equals zero. Now, if the degree of the numerator is equal to the degree of the denominator, so let's say the first term on the top was a x to the n plus yada, yada, yada. And the bottom was b x to the n plus yada, yada, yada. And you'll notice the degrees are the same. The limit is going to be the ratio of those leading coefficients. So the limit is going to be a over b. Now, if the degree of the top is bigger than the degree of the denominator, the limit is not going to exist because that graph is either going to go to infinity or negative infinity. And we can talk more about that as well. Now, these three examples are not rational functions. Rational functions are a polynomial divided by a polynomial. But these have fractional exponents. But guess what? The rules can work the same way. So in this first example, take a look at this problem. The highest exponent on the top you see is 3/2. The highest exponent on the bottom you see is 3/2. So if we look at both of those terms, they have equal exponents. I don't want to use the term degree, but technically, if these were polynomials, they have equal degrees. So the limit would be the ratio of those leading coefficients. It would be negative 2/3. Now, there is a little bit of a twist to this. You'll notice this limit goes to infinity. What if I gave you this same limit and it says as x approaches negative infinity for 5 minus 2x to the 3/2 over 3x to the 3/2 minus 4. Now, this limit does not exist. And you're probably thinking to yourself, well, why isn't it negative 2/3 again? We've got to be careful when you have even roots. X to the 3/2 is the same as x cubed, and you take a square root of that. Or you could say it's the square root of x cubed. Either way, you cannot take the square root of a negative. So this function doesn't even exist at negative infinity. All right? So it has a limit as you go to infinity, but it does not have a limit as you go to negative infinity because the function does not exist. Now, if you take a look at the next example, you should notice that the degree of the top is bigger than the degree of the bottom. And I shouldn't use the word degree, but it gets the point across. The exponent on the top is higher than the exponent on the bottom. So essentially, this limit is going to behave like negative 2 over 3, and the x's would reduce to x to the 1/2 on the top. So this comes out to be negative 2/3 times radical infinity, which goes to infinity because the top exponent is bigger than the bottom. This limit is not going to exist. It's going to go to infinity or negative infinity. In this case, it goes to infinity. Now, if I were to take this same function, but I'm going to let the limit of x approach negative infinity. Now, if I do this again, we have a rule. You have x to the 3/2. The 3x on the bottom is not a problem. You can plug anything you want in for x, but again, you cannot take the square root right there of a negative. So again, if we went to negative infinity, this graph would not have a limit. It does not exist because the function doesn't exist there. Now we're going to do one more, and I hope you get the idea about having the limits not exist at negative infinity. All I'm going to do on this next one is talk about the limit at infinity. Look, the highest exponent on the top is actually x to the 1/2. The highest x on the bottom is x to the first. So the degree of the top is less than the degree of the bottom. And again, I shouldn't use the term degree, but it follows my rules that the exponent on the top is less than the bottom. This limit should be 0. Okay? And again, the limit as x approaches negative infinity would not exist. Now, just so you know, this has a horizontal asymptote at y equals 0, but only at infinity. This one has no horizontal asymptote because it goes to infinity, and the other side there is no limit. The first problem, it definitely has a horizontal asymptote, but again, it's at infinity. The horizontal asymptote would be y equals negative 2/3. So you notice, even if the exponents aren't nice round integer exponents, we could still use those rules to find the end behavior. Now, let's take a look at a few more examples that are kind of crazy, and I'm going to start with the top two. Okay? How do we do these problems? Well, the shortcut is look at the highest degree exponent on the top and the bottom. So on the top, it's x to the first. On the bottom, it's radical x squared, which is x to the first. It's technically the absolute value of x, but as you go to infinity, it's just x. So the limit here would be 1. Now, how do we come across that work? Now, this is the algebraic way to think about it. What I'm going to do in this limit is I'm going to take every single term and I'm going to divide it by the highest power of x. Now, the highest power of x is actually x, because the square root of x is x. So the top I'm going to divide by x, and the bottom I'm going to divide by x. Now, I think it's pretty obvious to see that the limit, as x approaches infinity, if I start simplifying, this top is 1. But what do I do on the bottom to be able to divide by x? Well, what I'm going to do, I know as I go to infinity, the square root of x squared, because everything is positive, is just going to equal the x values. So I'm going to make this the square root of x squared on the bottom. So under my radical, x squared over x squared is 1, plus 4 over x squared. Now, if I plug in infinity, I'm going to get 1 on the top. I'm going to get radical 1 plus 4 over infinity squared, which is infinity. 4 over infinity is 0. So this would be 1 over radical 1. And you'll notice the limit is 1. So the shortcut works, and if you use that idea of dividing by the biggest power of x, you get the same thing. Now, what happens when I work with negative infinity? Everybody thinks, well, you take the top, highest exponent divided by the bottom, highest exponent. And let's just look at those two terms, because at infinity or negative infinity, that plus 4 doesn't mean anything. Now remember, we're going to negative infinity. And also remember that the square root of x squared is not x. It's technically the absolute value of x. It didn't make a difference over here because everything was positive. It makes a difference over here. This would be x over the absolute value of x. Now, as x goes to negative infinity, the top would be negative, the bottom would be positive, and they'd be the same number. So this would come out to be negative 1. So what's crazy is this function has two horizontal asymptotes. Y equals negative 1 is the horizontal asymptote on the left, and on the right-hand side, going to infinity, the horizontal asymptote is actually y equals 1. And if you looked at this graph, that's exactly what you would see. Now, what would the work be like? Well, remember, in this first step, we divided everything by x. Now, here's the thing. If we're going to negative infinity this time, negative infinity, that top x is negative. But when I put the radical x squared on the bottom, that's positive. So when I divided by x and divided by radical x squared, I really didn't divide by the same thing. How do I balance that out so both are negative? Well, let's just throw a negative on the bottom. A negative on the bottom sticks around, and by the time I get to the end, my answer is negative 1. So that would be the work if I was going to negative infinity. Two more questions here, and I wanted to mention these while we were talking about limits at infinity. This is actually the limit as x approaches infinity of 3/4 to the x. That's an exponential function. Now, when you studied exponential functions, if the base was less than 1, this was a decay function. Decay functions look like this. If you draw an exponential that's decay, it comes down and levels off at the x-axis. So the limit as x approaches infinity, well, you can take a look at it. It's going to be 0 because of the asymptote. If you multiply by 3/4 over and over and over again, it's going to get smaller and smaller and smaller, and it's going to go to 0. Now, just to change it up a little bit, what if for this same problem I asked the limit as x approaches negative infinity? Take a look at the graph again. What's happening on the left as you go to negative infinity? Well, there is no limit. The graph goes to infinity. That doesn't mean it doesn't have a horizontal asymptote. It's just the graph approaches that horizontal asymptote at infinity, but not negative infinity. Now, it's going to be the same thing when we talk about this next function. This is the limit as x approaches infinity of 5/4 to the x. Now, that base right there this time is bigger than 1. This type of exponential is a growth function. And what does a growth function look like when you graph it? It's going to start along the x-axis, and then it's going to get higher and higher as you move to the right. So this time when you look at the graph, if you multiply by 5/4 over and over and over again, well, that's just going to get bigger and bigger and bigger. It's going to go off to infinity. There is no limit as you go to infinity. But what if I said the limit as x approaches negative infinity? Well, look at the graph. It's going to go to 0. So again, there's a horizontal asymptote as you go to negative infinity, but not infinity. Now, I hope these extra notes on limits at infinity help you understand what end behavior is, help you understand limits at infinity. If you like this video, please hit the like button. If you feel like these videos are helping you, please subscribe to my channel. I'll be posting more videos as time goes by.